And now we come to our first concept question. If we assume that the orbit of the Earth about the Sun is a perfect circle, does the gravitational force on the Earth directed towards the Sun do any work on the Earth? And the answer is no, because at any point on the path of the Earth about the Sun, the force is always directed perpendicular to its motion. Now, in reality, the orbit of the Earth around the Sun is not a perfect circle. Rather, it is an ellipse with an eccentricity of 0.0167 to 3 significant figures. And this is easy to detect even without sophisticated equipment. The period from the March equinox to the September equinox is about 186 days, while the period from the September equinox to the March equinox is 179 days. This means that there are times when the angular speed of the Earth is greater than others, and this directly contradicts a circular orbit, which would predict a constant angular speed. This is very well explained in Kepler's second law. Not only do we know that a planet moves faster when it is closer to the Sun, but we also know that a line that connects a planet to the Sun sweeps out equal areas in equal times. And so the angular speed of a planet in its orbit is not constant, but the area speed, which is the change in the area swept out per unit time, is constant. And so there are periods of time for which gravity does positive work on the Earth, resulting in an increased angular speed, and there are periods of time when gravity does negative work on the Earth, resulting in a decreased angular speed. However, in the period of one solar year, relative to the Sun, the Earth completes a closed path. That is, it ends where it begins. And so the total displacement is zero, and hence the total work done on the Earth by gravity is zero. So let's quickly review instances of positive, zero, and negative work. If I have an object that is initially at rest, and I apply a constant force causing a displacement of that object, I have done positive work. Similarly, if I lift the object, I do positive work. However, if I simply hold the object a given distance above the horizontal, such that there is no displacement of the object, then even though I am applying a force to maintain the height, I am doing no work on the object. Similarly, if I lift the object and then place it at its initial position so that the total displacement is zero, I have done no work on the object. Now, if the object is initially in motion and comes to a stop due to the force of friction acting in a direction opposite its displacement and opposite its motion, then the force of friction has done negative work on the object, and in this case, the force does not directly cause the displacement. So let's look at a problem. A boy pulls a wagon with a force of magnitude F equals 50.0 newtons at an angle of 30.0 degrees with the level ground. Calculate the work done by the force on the wagon as the wagon is displaced 3.00 meters parallel to the ground. And for this problem, assume no friction acts on the wagon. So the work done on the wagon is the dot product of the force applied to the wagon and the displacement of the point of application of the force. This is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle theta between the applied force and the displacement of the point of application. And so this is 50.0 newtons times 3.00 meters times the cosine of 30 degrees, which to three significant figures is 130 joules, or Newton meters, which we can also express as 1.30 times 10 to the second joules. Now we can also use the algebraic definition of a dot product. If the force is given in terms of the unit vectors I, j, and k, and the displacement is also given in terms of the unit vectors I, j, and k, then the dot product of the force vector with the displacement vector is the sum of the product of the corresponding components, so that we have the I components, the product of the I components, plus the product of the j components, plus the product of the z components. So let's now look at an alternate version of the same problem. A boy pulls a wagon with a force F equal to 43.3 times I plus 25.0 times J newtons. Calculate the work done by the force on the wagon as the wagon undergoes a displacement, delta R, equal to 1.50 times I plus 2.60 times J meters. And again, assume no friction acts on the wagon. So once again, the work done on the wagon is the dot product of the force and the displacement of the point of application of the force. And so this is 43.3 times 1.50 joules plus 25.0 times 2.60 joules, which to three significant figures is 130 joules, or once again 1.30 times 10 to the second joules. Now we can use the equation that the dot product of the force and the displacement of the point of application of the force is equal to the magnitude F of the force times the displacement delta R times the cosine of the angle theta between the force and displacement vectors to solve for the angle theta between the force and displacement vectors. So we have cosine theta is equal to the dot product of the force and displacement vectors divided by the magnitude of the force times the magnitude of the displacement. And so the angle theta is the arc cosine of this quotient, the dot product of the force and displacement vectors, divided by the product of the magnitude of the force and displacement vectors. And so now we will find the angle theta between the force and displacement vectors in the previous problem. Now in the previous problem we have a force vector which is equal to 43.3 times I plus 25.0 times J newtons. We need to determine the magnitude of this vector, which is the square root of the sum of squares of its components. So the magnitude of the force is equal to the square root of 43.3 squared plus 25.0 squared in units of newtons, which to three significant figures is 50.0 newtons. the displacement vector, delta r, is equal to 1.50 times I plus 2.60 times j meters. And so the magnitude of the displacement vector is the square root of 1.50 squared plus 2.60 squared in units of meters, which to three significant figures is 3.00 meters. And so the angle theta between the force and displacement vectors is the arc cosine, or inverse cosine, of the dot product of the force and displacement vectors, which from the previous problem is 130 joules, divided by the product of the magnitudes of the force and displacement vectors, which is 150 joules. So this is equal to the arc cosine of 13 divided by 15, which to three significant figures is 29.9 degrees. So as an exercise, solve the following three-part problem. You push a toy car 0.500 meters across a horizontal desk with a horizontal force of 2.40 newtons, while the opposing force of friction is 0.600 newtons. How much work is done on the car by the applied force alone and friction alone? Finally, what is the total work done on the car? Now, in the examples that we have looked at so far, we have noticed that if the work done on an object is positive, then the speed of the object increases. If the work done on the object is zero, the speed of the object stays the same. And if the work done on an object is negative, the speed of the object decreases. Now, one type of energy that an object may possess is the energy due to its motion, and this is called kinetic energy. The kinetic energy K of a particle or a non-rotating rigid object of mass m moving at a speed v is defined to be equal to 1/2 the mass times the square of its speed. So let's quickly look at the units for kinetic energy. The standard unit for mass is the kilogram. The standard unit for speed is meters per second. And so the standard unit for kinetic energy is a kilogram times the quantity, meter per second squared, which gives us a kilogram times a meter squared per second squared. This is the same as a kilogram meter per second squared times a meter, which is a Newton meter, which is a joule. Now, when work is done on a system and the only change in the system is in its speed, then the net work done on the system equals the change in the kinetic energy of the system. This is known as the work kinetic energy theorem. Now, for a particle or a non-rotating rigid object, we have the following equivalent statement. The work done on a particle or a non-rotating rigid object equals the change in its kinetic energy. That is, the final kinetic energy of the object or particle minus the initial kinetic energy of the object or particle. This is the same as 1/2 times the mass of the particle or rigid object times the difference in squares of its final velocity and initial velocity.